welcome to the lectures on evolution of air interface towards 5G. So, we have been discussing about the multiple antenna signaling schemes which enable us to have higher reliability as well as provide better spectral efficiency. And we are looking at the diversity schemes. We have looked at receive diversity, we have looked at transmit diversity, both without channel state information at the transmitter as well as with channel state information at the transmitter. And then we have started looking into the diversity schemes where both the transmit and the receiver has multiple antennas. The scheme we have been discussing is dominant eigenmode. In the previous lecture, we have described all the details, procedures, where we said that we look at the channel in terms of its eigenvalue decomposition, whereby at the transmitter side we pre-code using V and we post process using U Hermitian. And since it is a diversity mode, that is only one value of signal is sent or one signal is sent, from the diagonal eigenvalues or the diagonal singular values, we take the one corresponding to the maximum eigenvalue. For this, we choose the vectors from U and V which correspond to the maximum eigenvalue and use them for processing. So, that particular one is used in the G, whereas this one is used in the transmitter. So, the vectors are formed accordingly. So, at the transmitter you have W, which is defined below, and at the receiver you process with G. So, G Hermitian, that is what we said, with U makes it 1 for this entry, because that is what we are doing. At the transmitter side, since we are sending only one value and there is only one column of the vector being unitary, this also leads to 1 and hence there is sigma max. So, the received signal is written in this form where n indicates noise and sigma max. So, basically the SNR is equal to Es into sigma max squared upon En squared, right, that is what we have. So, sigma max squared is the one which influences the SNR, and sigma max squared is equal to lambda max, which is the maximum eigenvalue of HH Hermitian, and hence SNR can be written as lambda max rho. So, let us look at the performance of such a scheme. So, this flat line is the one for the flat curve, rather is the one for CISO link. Then we have the result for 2 cross 2 Alamuthi scheme, and then finally we have the result for dominant eigenmode for a 2 cross 2 system. So, which clearly proves that this particular mode of transmission provides the best reliability in terms of error probability compared to other mechanisms which use 2 cross 2 transmission receiving system. So, after studying the error probabilities, we now look at the signal correlation model. That means, we have talked about the channel correlation or spatial correlation and see how does it affect the performance of the system. So, the average probability of error, we have described this in all our previous discussions, is given by a particular expression over here, and what we see is that there is the eigenvalues of R matrix which is present. So, we have a 2 cross 2 system in this case, and the eigenvalues of R are determined or are influenced by the correlation which is present in this R matrix. In case of HW channel, we have stated that lambda i's are equal to 1, whereas in case of correlated channel this will be not equal to 1, right. So, let us see that. So, under high SNR assumption, that means when rho is significantly high, under that case this expression can become Ne, as we see over here, remains as it is, and from the denominator term we can get this out. Of course, it is kind of lower upper bounded. So, this term comes over here. For high SNR approximation, this is a constant term. So, basically under high SNR you are going to get this product I equals 1 to 4. Under high SNR, this is approximately equal to rho d mean squared by 8 multiplied by, since you have the I over here, lambda I of r. Okay, so that's, so let's clean it and write it again. So what we have there is rho d mean squared upon 8 multiplied by lambda I of r, and since this is a constant term, it can be brought out. That is what has happened. And in case of which is non identity of r, so what we will get is this raised to the power of rank of r, because this product will only be to the rank of r, right, otherwise the rest of them are 0. So you are using only those within the rank of it. So for h equals to hw, of course we have said this is identity according to which we have derived the earlier result, and when r is fully correlated, R is all one matrix, so that means there is only one eigenmode and hence you do not get any diversity. So to see the effect of covariance or correlation, which is non-identity, you take a situation for simplicity that mr equals to mt equals to m, so that the analysis becomes easier, and then the eigenvalues of R, capital R matrix, are represented by this expression, which is kind of standard based on what we have been doing, and they are constrained to this. Right, that is a constraint that we bring into the system, meaning that the channel is restricted to a power of m. Right, channel does not provide any extra power than m. And using the arithmetic geometric mean inequality, which states that the arithmetic mean is greater than or equal to the geometric mean. So we apply it over here. So in this case, we have sum of lambda I over m, lambda I of r, I equals 1 to m, is greater than or equal to product of lambda I equals 1 to m raised to the power of 1 by m. So from this, what we find that this term is equal to 1, and hence what we have is the product of eigenvalues is less than or equal to 1. So that is the result that is shown here, right. So now what we see is that the product eigenvalues, that is less than 1. So we have that term here, which is 1 upon pi lambda I r, I equals 1 to rank of r, right. So that is what we have. So what it means is that this denominator term, because there is this inverse over here, this term is greater than or equal to 1. That means the whole ratio is less than or equal to 1, right. So if the denominator is greater, sorry, we wrote it wrong, this denominator is less than or equal to 1, that means this ratio is greater than or equal to 1. So that means this multiplicative factor is something which is greater than or equal to unity. It will be equal to unity under the case of HW channel. So this probability of error expression, which we are outlining with the box, is multiplied by a factor which is greater than 1, which in turn means that the average probability of error increases if R is not an identity matrix. So if R is not an identity matrix, in that case we see that the error probability increases. So to check the performance, what we see that under no spatial diversity, we get the CISO link. What we see over here is that this line that I am drawing is the one which is without any spatial diversity, and the new curve that I am tracing is the one which is with IID, that means independent identical or identically independent fading, which means that is independent, there is no correlation. So because of a certain amount of correlation, what we find is that the error probability curve has shifted upwards. So there is an upward shift in the error probability curve which I am tracing by the blue colored ink and thickening the line. So, that clearly shows that the error probability increases because of correlation present. So, correlation is not beneficial for error probability, and whatever error probability one receives under HW channel becomes only worse. So, that means it increases when it is not an HW channel, right. So, that is the important summary that we get in studying the signal correlation. So, once we have discussed about the diversity, it is very important we move into the next set of things, that is the capacity, which is one of the most interesting aspects why MIMO is so popular. Of course, there is one more interesting aspect in the new generation, that is beamforming, but the biggest advantage that MIMO has brought in over the last few generations of communication systems is enhancement in capacity. And we are going to study the system under frequency flat fading conditions. This is what we have mentioned earlier. So, also slow fading condition and all the MIMO assumptions that we have made before. So, for a typical MIMO link, A empty matrix, and what we have is MR cross empty matrix. Y is a MR cross 1 receive vector. S is an empty 1 cross empty cross 1 signal vector. Okay. So, what we have is the received signal in its linear equation form. Y vector is some scaling H matrix S vector plus noise, and it is also given that RSS is the receive or the signal covariance matrix with a constraint that trace of RSS is equal to empty. This is an important constraint. So, the total average transmitted energy constraint, that means we do not want to use excess transmit power, and what we see over here from this part is that the transmit power is equally divided amongst the empty transmit antennas, right. That is what we have over here, and then if we constrain that trace of RSS is equal to empty, then we will ensure that the total transmit power is restricted to ES. That means we can compare the performance with the CISO link. So, the capacity of a MIMO channel is the one given by which maximizes the mutual information between the received signal and the transmitted signal over the distribution of the transmitted signals. So, Fs is the probability distribution of the vector S. So, this is a standard result which we will accept. We cannot afford to go through the derivation of this. It is available in standard textbooks. So, now let us focus on this mutual information expression. The expression for mutual information is given as the entropy or the differential entropy of Y, because this is a continuous random variable. Take away the conditional differential entropy of H, that means the differential entropy of Y given S, right. So, that is the expansion of the mutual information, and we have also defined both the necessary terms. S, the signal S and noise are independent. This is one of the assumptions, it is kind of obvious, but still it is important, which leads to the condition that H of Y given S, because Y is equal to H S plus N. So, we could write that differential entropy of Y given S is equal to that of H n, right. So, because we are saying that H S plus N conditioned on S, this is what we are trying to evaluate. Now, since N and S are independent, here you do not have any uncertainty. So, what is left with is uncertainty between H of N given S. So, H of N given S is basically H of N, right. That is what we have over here. Now, we get back to the original equation, that is this one. So, we have I S semicolon Y, which is the mutual information between transmit and receive signal, can be expressed as H y minus H n, where H indicates the differential entropy of the received signal and Hn receives the differential entropy of noise. So, now if we see the capacity expression, it is maximization of the mutual information, right. That means maximization of this term. If we look at the right hand side, we do not have any control on the differential entropy of noise. It is a natural event. So, we only have control, possible control over differential entropy of the received signal. So, therefore, we say that the mutual information is maximized by maximizing the differential entropy of the received signal, because the received signal is connected or is controllable through the transmitted signal S. With this we proceed. So, the differential entropy of noise is mentioned over here, which is fundamentally controlled by N naught, which is the noise power spectral density. IMR, or you can say that MR is another parameter, but we have seen that as MR increases, the received signal to noise ratio increases. So, we would like to have MR as much as possible. So, therefore, we use this definition of differential entropy for noise. Similarly, the differential entropy for Y can be written as given over here, where RYY is the term is the covariance of the received signal, that is expectation of Y Hermitian. So, now let us expand Y Hermitian over here, that is, if you take y equals to square root of root over Es by mt Hs plus n. So, you are going to multiply this by the Hermitian of the same term. So, you are going to get noise Hermitian, you are going to get root over Es by mt S Hermitian H Hermitian. So, this product is what you are going to get. So, if you expand the terms, you are going to get Es upon mt, and then you are going to get H S S Hermitian H Hermitian plus you are going to get N Hermitian, and you are going to get the cross terms, that is H S N, and of course, the root part is there, and the root over Es by N naught times S Hermitian H Hermitian noise, and of course, the Hermitian. So, these are the terms that you are going to get, and then you have this expectation operator. So, if you apply the expectation operator, it would not apply on this, that is constant. H is given, that means for a particular value of H. So, E would operate on SS Hermitian, and E would operate on this, as well as E would operate on this. So, E, what we have stated that S and N are independent. So, what we would get is Es times En. We have said that En is 0, and hence this term would go to 0. The fourth term would also go to 0. So, we are left with the first and second term, that is Es upon mt H. So, E of SS Hermitian we have defined earlier as RSS H Hermitian plus E of NN Hermitian. Again, you can write this as RNN, which you can write it as I N naught, of course, I MR times N naught. So, what you see over here, this term is available here and this term is available here. So, we have got the expression of RYY. So, now if we have to maximize the differential entropy of Y, what we are left with is we are left with this expression where H is something which is not in our control, it is from the channel. Noise is something which is not in our control, it is again from the channel. So, the only thing that is left with us in our control is RSS. Therefore, we can say that as you are seeing that differential entropy is given as log determinant. So, log determinant of RYY. So, what you have is log of determinant of RYY minus log determinant of, you can say, RNN, you can say it that way. So, you have determinant of RYY upon determinant of RNN and a log outside that. So, if you expand this in terms of these expressions, you will end up in the expression over here where there is IMR ES by MT N naught H RSS H Hermitian, and therefore, you can state the capacity as the one which maximizes the mutual information, that is maximizes this entire expression over trace of RSS or over RSS with the constraint that trace of RSS is equal to MT. So, that means the capacity expression, to make it look clean, we have as given there. So, that means it maximizes this expression. Let us change the pen color. It maximizes the expression over here. Of course, it is the log determinant over the over RSS with the constraint that trace of RSS is equal to MT. All right. So, this is also called the error free spectral efficiency. So, in all the analysis of MIMO that we do here on, we will be using this particular expression for all our right. So, the first thing that we discuss is the situation where channel state information is not known to the transmitter. That means, CSI is not available at the transmitter, right. So, if CSI is not available, then that means at the transmitter side one does not have any information about the channel. This is opaque, one does not know what is going on in the channel. So, there is no specific information about the channel. So, the best that one can do is set RSS equals to IMT, right. That means, you just divide the power equally and you have no other option to do, and S is non-preferential. That means, you do not have any partiality over the selection of S. So, that means, you have already chosen a condition on RSS, and if we go back, we find that your trace has to be constrained to MT, but RSS can be of any structure. So, the particular structure of RSS that we have identified is IMT. All the diagonals are 1 and the matrix is of size MT cross MT or MT order identity matrix, whose trace is definitely equal to MT. So, now we see that so the constraint is gone. So, C is equal to log determinant of. So, in this we had RSS, and since that is set equal to IMT, it kind of vanishes from the equation, and the rest of the equation as it appears over here is the expression for the capacity under such situations. What we now do is H Hermitian is a symmetric matrix, and therefore, it can be factored into a structure like Q lambda Q Hermitian, where Q are orthogonal matrices and lambda contains the eigenvalues of H Hermitian, right. So, now we can write the capacity as log determinant, that means, we have not changed this part. IMR also remains as it is, ES by MT N naught remains as it is, and H Hermitian gets replaced by Q Hermitian, Q lambda Q Hermitian, using an identity of determinant and also using the condition that Q Hermitian equals to IMR. That means, we will swap these two positions, you are going to get Q Hermitian, and then again you are going to swap the positions, you are going to get Q Hermitian Q, that will be let equal to identity. So, what you will be getting is log determinant IMR ES by N naught, you will be left with lambda. This entire matrix, as you can see, is a diagonal matrix, because this is a diagonal matrix with constant multiplicating terms. So, IMR is all ones, and this matrix is ES by MT N naught and lambda 1, lambda 2, so on. So, that is it. So, that means, this whole matrix is a diagonal matrix whose determinant is a product of 1 plus ES by MT N naught times lambda I equals to 1 to rank of R. So, that means, rank of R, you can set it equals to R. So, determinant of this and a log base 2. So determinant gets changed to a product, right. So, this would translate to sum of log base 2 1 plus ES. We will of course erase these things, okay, so that we get a cleaner place. ES by MT n naught multiplied by lambda I, and I goes from 1 to R, which is the rank of the matrix, and this is the expression that you have over here, right. So, where R is the rank of the matrix and lambda I go up to R, and ES by MT is the transmit power, right. So, what we see is that if we look at this particular part, is a seesaw link, that is, this is the capacity of a seesaw link, and we are summing over the capacity of a seesaw link. Each of the seesaw link has a strength corresponding to lambda I. So, that means we can say that in this case it is the sum of the capacities of R number of seesaw links or seesaw channels, each with a power gain of lambda I. That means the very important situation that we see is that MIMO opens up multiple scalar spatial data pipes or modes, and this is exploited in providing high amount of spectral efficiency. In seesaw, you have only one data pipe where your SNR is inside the logarithm. Here what we see is that this is broken down, the signal power is broken down, and we have added them. That means the summation is outside the log. So, that means now the power is distributed to different seesaw links, each seesaw link having a certain amount of gain, and the transmitted power against each seesaw link is an equal power, that is ES by MT. So, all one needs to do is to compare this and see whether it gives an increase in power, and the clear cut answer is this gives a much increase in signal in spectral efficiency, that is much larger value of spectral efficiency than a seesaw link, which has all the power entrusted inside the logarithm. So, this helps us grow beyond the logarithmic growth of spectral efficiency. So, this is a very important result that we have arrived at. We will continue to discuss the capacity of MIMO channel when channel is known to the transmitter, as well as look at the beam forming techniques which help in providing high capacity for MIMO with advantage of millimeter waves, where you can provide a much more focused beam in the next lecture. Thank you.